AI4REAL networks. And herein, I'm going to share with you some of the preliminary results and also some future perspectives for the project. So just to mention that there are about 14 partners in the project from 8 different countries in Europe, and also different industrials and research and technology centers in Germany, in France, and Portugal, and other countries. So it's a collaborative project in Europe. And I'm going to present first the objectives of the project, afterwards the different work packages, and also the results corresponding to each of these work packages. Finally, a sustainability plan of the results of the project that we have already pushed to the Linux Foundation, and finally some concluding remarks. So what are the main objectives of this project? As the name says, it's related to the decision-making process for critical infrastructures, which are air traffic management, electricity networks, and railway networks. And the aim is to push the boundaries of reinforcement learning and supervised learning for these structures, which is very in a high stakes importance of security, cybersecurity, and risk management. And also the trustworthiness is one of the main keys of this project that should be considered in every design, in every step of the design of different algorithms and frameworks. So we have considered 3 modes of interactions between human operators and AI agents. So it's a project that is based on human-centered decision-making, and the AI is just to assist the human during the decision-making process in different industrial contexts. And also we have an interaction mode of co-learning, that is the human learns from AI, and AI can have some feedback from human operators to improve the policy and its a recommendation in future steps. And also we have an autonomous AI where human could play a role of supervision over the AI in catastrophic, for example, situations. So all the algorithms of this project are open source, and we would like also to boost the development and validation of new AI algorithms for this project. It's based mainly on digital environments. That said, we use the synthetic data simulations for example, testing and training of the model, but we have also the aspect of evaluation of real-world data scenarios. So in a nutshell, this project has 2 main objectives. The core research and development is based in work package 2 and 3 of the project, where we have the different type of reinforcement learning algorithms, for example, knowledge-assisted AI, where it is important sometimes to include also the expert knowledge from human operators, heuristics, well-known heuristic industry, or physical equations into the design of the AI algorithms, and also to have some scalable reinforcement learning algorithms, like, for example, distributed or hierarchical. For example, if the data or scenarios are distributed in different countries or different regions, so it's important to have the algorithm that could integrate that during the learning. And also the transparency of the AI algorithms developed. For example, these algorithms should be explainable, and also to be able to measure the level of the uncertainty when we are predicting or recommending, have some recommendation from the AI agents. And in work package 3, we have a collaboration between AI and human operators, where, as I said, there are different levels of interaction between AI agents and human operators, where, for example, the AI recommendations could also be based on cognitive load level and attention level of human operators. By measuring, for example, the different stress levels of human operators, the AI could adjust its recommendations based on that. And also the co-learning that also I've mentioned in the previous slide, where the human operator and AI learns from themselves, and they can complete their advantages to have a better decision making, and also as a supervision where human could supervise the AI for some automatic tasks. And finally, we have the validation of these results. Once we have different models, we should also be able to validate them on real-world scenarios. And for that, we have also some human-centered evaluation KPIs that I will present in future slides, and also that the recommendation and decision-making process should be compliant with the regulations and specifically with AI Act and also Altai platform framework. And also we would like to measure the economic impacts of these results of the projects. So the project, as I mentioned, is structured in 4 work packages. The first work package was to design a holistic framework for interactive AI, that is the interaction between AI and human operator for decision making. And also that is where we have defined the different use cases for our 3 industrial domains, which are the critical infrastructures, work package 2 and 3, which are more theoretical and algorithmic parts of the project, and the work package 4 is more on the validation and evaluation aspects. And work package 5 and 6 are more on dissemination and project management aspects. So I'm going to start with work package 1 on the definition of the use cases, KPIs, and also the framework of the project. So in order to define the different use cases for this project, we have identified a set of requirements and also the KPIs by following the assessing list for trustworthy AI, which is Altai framework, which has different lines that you know maybe that should be respected during the design of these use cases, the requirements, and also the metrics, how to evaluate the different criticality in different use cases. And based on that, and also a template from some standards, we are able to define 6 use cases, 2 per industrial domains, based on these templates. And also for each use case, as we would like to also to have a variability in terms of interaction between AI agents and human operator, we have also considered this level of autonomy of AI in the design of the different use cases. So here we have 2 use cases, for example, for power grids in the left-hand side of the use case list. So the first one is AI assistance supporting human operator decision-making in managing power grid congestions. That is where, for example, if we have some congestion, power line disconnections in power grids, that is, we would like to have some topological actions in the grid to remedy this congestion and also to not have some overloads in power line and to avoid the cascading failures or the blackouts. So in these situations in power grid, they don't want to have autonomous AI. So for them, the role of AI is just to recommend, to have some recommendations for human operators. And for railway, for example, we have the automatic rescheduling in railway operators and also rescheduling in railway operations. And for them, there are some tasks that could be completely done by AI, by human supervision, human as supervisor, or with co-learning tasks where the human and AI should collaborate together to have a final decision. And for ATM, air traffic management, also we have some mode of interaction that is AI recommendations for human decision making or collaborative mode, which are the sectorization tasks and flow and airspace management assistance. And concerning the conceptual framework of this project, that was a collaborative work with different partners from different domains. So there are the mathematicians, the philosophers, the psychologists in the project, and we should respect each step of the design, of the system design, for example, the overarching level, and also some trustworthiness and ethics. And this collaboration have made possible the design of the conceptual framework at the first step, where we have some context and decision environment, which provide, for example, the different scenarios for railway, power grids, and ATM. And also there could be some events that come from the environments. And when we have some critical events, the human operators and AI agents should collaborate with one of the, for example, mode of interaction that I've introduced in previous slides to have to propose an action for that critical events that could solve the problem. And once we have an action that has been proposed by this collaboration mode, that should also be compliant to some trustworthiness properties. For example, that should be robust, transparent, and also to respect some regularities, for example, the risks and ethics and the other notions of trustworthiness. So we have adopted a system engineering approach, like model-based system engineering to firstly identify the operational, functional requirements using the stakeholders diagrams, abstract base user stories, and also environment diagrams to identify the interaction between different modules, which are, for example, the environment, the context, and the operators, the human operators, for example, the data profiles, and also the standards, which are very important for this project to develop the conceptual framework. And that helps to build the block for the conceptualization of this framework that I already presented. But if we zoom a little bit inside each of these blocks, for example, for human operator, here the objective would be for the AI agents not only to recommend some actions, but also to allow the human operators to explore more possibilities, to, for example, to animate the human agents during the decision making and not result to some de-skilling of human operators to just rely to AI without any attention, and also to provide some transparency, for example, during the recommendation, and also the mirroring of the human behavior during the decision making, such that the human could see how he behaves during the decision making and he can improve his mental model about himself, about the AI, to trust to the AI model, about the environment, and also about the interaction with other humans in the decision making. So it's a process of continuous learning of the human agents and also to motivation for the human to increase their situational awareness for decision making. As I mentioned, there are also different trustworthiness assessments properties that we are required to respect in this project, like risk assessment, the fairness of the decisions, bias mitigations, security and privacy, accountability, and legal compliance. And now if we zoom on the AI-based agents block here, we have more, for example, the preparation of some recommendations for AI, for human agents. Based on these recommendations or assistance, human agents would send some feedbacks to the AI, and AI could take into account these feedbacks from human operators to improve and calibrate these parameters to have more adapted recommendations in future for this human. And also these recommendations should follow some AI model properties or trustworthiness properties like robustness, for example, to some unseen situations, or to, for example, adversarial attacks and resilience. For example, if there are some changes in the behavior, they could have some resilience in these changes, reliability, and also the traceability of the AI recommendation, the generalization to out of distribution, for example, examples, or scalability to, for example, other types of grids, or bigger grids, power grids, or, for example, railways, and also to have some sort of uncertainty quantification. And based off this uncertainty quantification, where some of the recommendations of AI agents are not very certain, so the human agent could refuse them or have some feedbacks to AI agents to improve their predictions in future. And I have also here a demonstration of this framework that we have implemented for power grids. Here, for example, in the context window in the middle, we have a power grid, which comes from a power grid simulator, which is called grid to that is visualized. And in the left-hand side, we have some events that come from the context. For example, we have some risk of contingency in power lines in future. So we use some event anticipation. So there are some AI solutions which provide some forecasting for future critical events, and human operators could watch them and see some KPIs concerning, for example, these critical events. For example, here there could be some disconnected lines which are shown by dashed black lines, and also some overload problems which are shown by red lines on the grid. So the next step, when we have some critical events that come in the alerts pane, the human agents should provide some decisions. And for that decision, they could request AI agents for some recommendations, and AI agents provide some recommendations and also provide some KPIs for each action that has been recommended. And human agents, for example, thumb down for some of these actions to say that they are not satisfactory for the current situations, and apply one of these actions which are best with respect to the KPIs that have been calculated for this recommended action. And when this action has been applied, so the red line is going to orange, that is, we have solved the overload problem in the grid. So that was the first work package that where we have defined the conceptual framework, and also we have implemented this framework for a power grid use case. A second work package now, which is more on fundamental AI building blocks. Here I give an example for knowledge-assisted AI power flow simulation that I worked on myself during the project, where the objective here was to replace the costly physical solvers for computation of power flows. For example, in the real world, the human operators should run 1 million or hundreds of millions scenarios as the simulations to, for example, examine the impacts of their actions on the grid. And that's very costly when we are using the physical models. And the objective is to replace these physics models with AI, with machine learning, to accelerate them. But the disadvantage of doing that is the machine learning approaches are not respecting by design the physical constraints which are formulated using, for example, some power grid equations during the optimization step of physical models. So here the objective is to solve these optimization equations using machine learning, that is to consider them as constraints during the optimization of machine learning or AI algorithms. So here a power grid is shown using the nodes and edges, and we can very easily transform them to a graph with some nodes and edges. That is like here. I use some algorithms in state of the art for, like, for example, graph neural networks. So to demonstrate that, here is the formula, for example, for a power grid, where we have a conservation energy, that is the difference between the production and load into a grid should be equal to the sum of the powers coming from adjacent or neighborhood to this node. And that is one of the Kirchhoff laws, that is the quantity of the energy entering the node should be equal to the quantity of the energy going out from that node. And so that's we can manipulate the graph neural networks to represent these quantities that come from neighboring nodes, like the message passing mechanism. So the multiplication of the feature nodes from the neighboring and by the messages on each edge would be have a physical sense. That is, the message coming from the neighbors have a physical meaning. This is the power that comes from the other nodes. So that helps to have an optimization objective for a machine learning algorithm, which is the graph neural networks. By solving that during different iterations, hopefully we are going to optimize the values, for example, for voltage angles, and also different quantities of the power flow on the grid. So it's a full architecture that is demonstrated here, where we have some graph neural network layers, which are interleaved with local conservation layers, where we compute the physical constraints in local conservation layer. And at the end, we would like that the algorithm to be able not only to have the precise and accurate power flow predictions, but also to respecting some physical constraints. So it's a sort of physics-informed graph neural network. So to evaluate that, we have also designed different scenarios. For example, for training and test data set, we have generated some observation and scenarios with only one disconnected line. And for out-of-distribution evaluation, we have considered some scenarios with two disconnected power lines. And that changed completely the dynamic of the power flow in power grids when we are introducing more disconnected simultaneous power lines that would enable the assessing of the robustness of the models. So when we have evaluated these, for example, graph neural network, and we have compared with a simple fully connected architecture, which is densely connected without considering any topology and physical notion in the design, we have seen that with using this fully connected, we have some errors for different physical laws. For example, we have the loss positivity, which is very high for error for this, and also the global conservation and local conservation, which have 91% and 88% of error. However, by using the graph neural network, we were able to respect all the physical laws and to have some precise predictions. And that was the same behavior also for out-of-distribution test data sets, where we have some distributions which are very different from the training and test data sets. And we have seen that the graph neural networks, which were trained with some constraints, were able to have some precise and to respect the physical laws with some very minor errors for local conservation. And also for this specific use case, we have also in the past, we have organized the competitions where we suggested a bigger grid with 118 nodes, and with introducing also some renewable energy sources like wind and solar. We had also different results based on, for example, physics compliances and machine learning, for example, accuracy, speed up, when we are using AI solutions with respect to the baseline, which are physical solvers. We have seen that there were some interesting results in this competition that improved the baseline, the physical baselines. And so I'm going to continue with other contributions in the project and to give you an overview. For these, for some of these contributions, I have some details, but for others, I can give some explanation, but I'm not expert in all of these approaches as they have been developed by different partners in the project. Another algorithm that have been developed was also exploiting the expert knowledge, which is a reinforcement learning based algorithm. For example, it's the exploiting or extending the deep Q algorithm. And by constraining these algorithms by integrating some expert knowledge from human operators. For example, we have some scenarios where human operators could inform that some zones on the grid are more susceptible to have more or better actions to provide for an agent. So we restrict or constrain a region of the grid for the AI agents to look at during the exploration phase of the reinforcement learning algorithm, and RL agents pick only the actions in these restricted areas during the exploration phase, which are informed by expert knowledge. And there were also some hierarchical and distributed reinforcement learning that have been developed in the project, where, for example, for railway domain, we have the trains where they are, each train is considered as an agent, and they have considered that they have modified the Q-learning based optimization or reward algorithm, where they have added also a maximization over the Q value, which considered, for example, an agent, another agent, adjacent agent in the grid. So it allows to have some sort of the distributed Q learning, where we have some agents that are communicating over this reward to maximize this reward at the end. There are a lot of other contributions. For example, there are some safe reinforcement learning algorithms, where they provide some sort of assurance of the convergence in safety critical control, which has also some contribution in NeoReps, and also some imitation learning using soft label. That is, instead of just suggesting an action at the end of reinforcement learning algorithm, we are going to suggest multiple actions, which could all be good. And so it's not only just one action that could be proposed, but a sort of a probability distribution over different good actions that can reduce, for example, the overload or the different problems on the critical infrastructures. And the other contribution that is interesting also, it was TraceRL, that allows to trace or replay the scenarios using a what-if visualization. Once an agent is trained, and human operator could play with the scenario, for example, and at each step or each time step, he could select a different action and see the result of the action in the grid. So it could trace the different actions suggested by the AI agents, for example, to have more transparency and to traceability of the procedure. Another aspect was the transparency and trustworthy AI, where human assessment module that has been developed in the project, where we measure the stress and cognitive load of each human operator. And this information could be used, as I mentioned earlier, by AI agents to readjust their recommendation during the decision-making process. For example, a model would exploit some ECG or cardiovascular information of the different personnels or human operators, and it's very personalized, the models per person, because each person has different characteristics. And once this personalized model has been learned on a human operator, it could provide some information during the decision making, and, for example, to set the interaction mode to autonomous if the human operator is very busy, he has a cognition load which is very high, or a stress level is very high, to adjust also the interaction mode between the human and AI. And also we have some explainability panels, for example, for power grids, where we can, for example, for each recommended action by the AI agents, compute some statistics, like, for example, the improvements of the overload when we have some recommended action from the AI agents, that the human operator could monitor these KPIs, these statistics, to select the best actions during the decision making. So all these developments are open source and are available also on the GitHub repository of the project. Now the third work package of this project, which is AI augmented human decision making, which is really the interaction between AI agents and human operators. For package 2 was more fundamental AI block. There was no interaction between human operators and AI agents, but this work package focused more on the interactions between these two agents, human operators and AI agents. So there are some questions. We can explain this diagram with some guiding questions. For example, how to go from autonomous AI, which was the objective of work package 2, to AI assisted decision making. That is how, for example, the human operator could request from the human agents, or human agents could request from the AI agents some recommendations, as we have seen, for example, using interactive framework that human agents in real time could select some actions, and how to predict the epistemic and aleatoric, for example, uncertainty when we are using the AI agents, how to deal with multiple and sometimes competing objectives. We have also the notion of multi-objective reinforcement learning when we have some competing objectives, how an RL agent could solve such problems, and different objectives also, that is how can humans interact with AI in real world, for example, to solve a problem. How can AI learn from humans by have some, for example, feedbacks from human, and how can humans also learn from AI? So these questions are organized in different tasks of this work package. And yes, at the end, we have also some autonomous AI and how humans could supervise the autonomous AIs. So for the first contribution, that was how to predict the epistemic and aleatoric uncertainty. These uncertainties already integrated in one of the works that have been done by some colleagues, and it was also to predict the probability of the AI agent failures over future time horizons. It's very important to see, for example, with which probability the AI agents could have some failures in future. And for that, an LLM algorithm have been developed that is imitate an ML model, a machine learning, to generate some interpretable outputs that informs, for example, humans about the conditions under which the AI recommendations may fail. So it's very interesting that to have some mode of transparency of AI models, that when they are going to fail, and to give the humans the opportunity to know them in advance. And also the other is the conformal prediction framework that creates some bounds over the predictions made by AI agents, so the human could see this level of uncertainty during the decision making, and also the risk assessments. And the other one was the multi-objective decision making and reinforcement learning, where modification of policy-based optimization algorithms have been made, where instead of have one reward, we have various rewards. For example, the efficiency of the algorithm with some different objectives that could be optimized in parallel. And so the algorithm doing the optimization should be able to optimize all these objectives. And in order to that, there is also a Pareto optimal. For example, at the end, we could see if they respect the Pareto optimal. If not, this iteration of optimization is repeated until we have some optimal solution with regard of these different objectives. And also to manage that how AI can learn from humans, we use some sort of inverse reinforcement learning, that is from some scenarios that have been played by human operators in real world. We are going to use the inverse reinforcement learning to learn the rewards from these scenarios. That is, we have some observations and actions that are already existing, and the objective is not to learn the recommendation, but the objective here is to learn the reward function. That is the intent of the human at the beginning of the optimization. So that is how that AI could learn from human operators, for example, one way to do that. And there are also different research questions in order to generalize the inverse reinforcement learning to different, for example, use cases, for example, scaling to continuous SLS spaces, the model risk-sensitive behaviors, and other remarks which are under review, or they've already been published in different conferences. And for the interaction mode, that the collaborative work between human and AI, here is a use case of ATM. That is, we have the sectorization problem. In sectorization problem, we would like to define the air sectors where we have in each sector, we have some constraints. For example, the number of airplanes in each sector should respect some constraints. And also, for example, each sector is supervised by a controller, by air traffic controller, and the charge of this air traffic controller should be managed by the number of airplanes present in each sector. And the definition of these sectors could be a collaborative work between AI. AI could suggest, for example, some sort of the initial sectorization and with respect to multiple objectives. Here is a Pareto front that is visualized in the graphic here, and the human user could select one of the points here that respond well to his requirements, and also to have some assistance, direct assistance from AI, or to chat with AI to have some recommendations on these points. So it's a mode of collaboration between AI and human, and to somehow have interaction to solve the real world problem, which is the sectorization for air traffic management. Finally, how humans could learn from AI. And also there are various works that have been done, for example, for railway, for example, that could be made through the transparency of the AI algorithms that could support the human motivation, or informing, for example, providing some support for human learning and also continuous improvements in complex network control tasks. An example of that is in railway. For example, there is another framework where human operator, for example, could manipulate an environment that has been managed by AI agents. And for example, by modifying some parameters of the agents, for example, to stop one and to pause the simulation to see how one manipulation can affect the behavior of other agents, and a mode of interactions during which the human could learn from AI. So the AI play the scenario and human observe and learn from by modifying the different properties could learn from that. Finally, the last work package of the project, which is more on evaluation of trustworthiness and the different performances of AI agents. For that, we have 4 guiding objectives. The first one is to evaluate the quantitative KPIs, that is technical performance and scalability of the solutions that have been proposed in work packages 2 and 3. And the second one is to assess the robustness, safety, and resilience of AI agents. The third one is to evaluate the human user experience and the acceptability of the AI recommendations by human operators, and also the trustworthiness properties. Finally, we would like also to study the economics and regulations of the AI solutions. So this work have conducted to identifying multiple categories of KPIs for each of these 3 objectives. For example, for the first one, we had identified the solution quality, scalability, effectiveness that I'm going to present after. And we have also classified them with respect to different industrial domain. There are some common KPIs, but we have also some very specific KPIs per industrial domain that should be managed. In order to be able to evaluate these KPIs on different solutions that I presented during the second and third work packages, we have also designed a pipeline, evaluation pipeline, where the entry of these evaluation pipeline, which is also guided by different objectives of the evaluation for this project, are AI models and the different scenarios for each industrial domain. And these AI models are evaluated through the different validation campaigns in the project, which is an automatic pipeline that we have implemented in the project. Finally, we score each contribution based on the aggregation of different KPIs. So we have selected a list of KPIs per scenario, and we aggregate finally to have a ranking among the solutions. And we have different type of tests, different type of evaluation. As I mentioned, we have some technical KPIs. These technical KPIs could be computed completely automatically using some algorithms, for example. But there are some KPIs which require to design some experiences and behavioral analysis of the human operators. For example, there are psychologists that are going to provide some questionnaires to human operators and to analyze their behavior when playing some scenarios in real world, and to see, for example, how they are going to interact with AI, how they accept the AI recommendations, and how they could, for example, improve their own behavior, and how they could provide some feedbacks to AI agents to have better recommendations in future. So there are some automatically score results and some manually score results that could be entered in this pipeline. Finally, to have some score for all, which is a combination of these two KPIs. And to define different KPIs, we have also used some templates from the standards where every KPI in this project, which are about 60 KPIs, for each of them, we have exactly the step-by-step description of how they should be defined, what are their objectives, what are their formulas, what are the steps that we should follow to be able to implement them. And for example, for technical performances, we have the effectiveness, which is how efficiently does the AI achieve the intended outcomes with optimal use of time and resources. For that, we have, for example, reduction in delay. For example, the reduction in delay KPI aims to quantify the time gained overall and for each airplane with introduction of AI. So if introduction of AI helps to reduce some delays in management of air traffic management. And we have also punctuality, for example, that is the percentage of trains arriving on time when we are using some recommendation from AI. And the solution quality, the second one is, for example, does the AI deliver accurate, relevant, and well-suited solutions that meet user needs? For example, the carbon intensity, the operation score, network impact propagation, and other stuffs. And finally, the scalability of the recommendation, for example, or the AI agents. That is, for example, to see if they are able to have some scalability over test time or training time.
Milad, to interrupt, I don't know how much time you still need more, but maybe if you can make it for 1 or 2 minutes to be appreciated for questions. Thank you.
All right. And yes, here is some evaluation objectives also for robustness, resilience, and reliability that I mentioned before. We have also defined some pipelines to how compute this robustness, for example, criteria in different scenarios. And we have developed some, for example, adversarial RL agents per industrial domain to be able to introduce some perturbations and to see how the AI agents could behave in these perturbed environments. And also we are interested in domain shift. That is, at some times we can have some perturbation that change completely the distribution for a while. We would like to see how the RL agents are able to adapt the strategy to this distributional shift, and how much time that takes for them to adapt their strategy. And finally, there are some socio-technical decision quality and trustworthiness properties here. For example, we would like to see the perceived decision novelty, how the recommendations, for example, are novel for human operators, the acceptance of human operators towards the AI systems, to measure for example, the human user experience. through the cognitive and stress criteria that I presented before, and also to measure the human motivation and to see how human could learn during the interaction with AI, and also how the task could be balanced between human operators and AI agents. And all of these could be measured through the interactive framework that I presented before. We are capturing the different logs from the human behavior. For example, the human response time, the number of clicks on the screen by human to measure their level of stress and cognition. And also there are some variable objects that could also measure these quantities. And also that to say that AI4REALNET also aims to have the sustainability plan. That is, we have pushed the different contribution to Linux Foundation for open sourcing, and for that after the project lifetime, so the impacts and benefits for stakeholders and community and society could persist. That's an example of that for public grids. And finally, the conclusions and perspectives. So it's, as mentioned, it's a project for human-centered decision-making with AI assistance, and where different mode of interactions are very important for this project. And the role of AI here is to increase the cognitive process of human operators and not to replace them. It's not possible to do that in some critical infrastructures. For perspective, we are aiming to execute the different validation campaigns to capture the technical KPIs and also the socio-technical ones, and also organizing some competitions per industrial domain. So it's all about the presentation. Thank you for your attention.
Thank you very much to you, Milad, for this very interesting and dense talk. So yeah, it's time for questions now. Please feel free to raise up your hand, or you can even ask Milad directly. Maybe I can start, Milad. I have some questions. The first one is more general. What is about the open source principle within this project? It is expected we get some open source pieces from that, yes. Including maybe use cases, because you mentioned some use cases that would be on the open source. Yes.
Most of the use cases that are used in the project are based on synthetic data, which are generated using digital environments. So they are the scenario is going to be open source. And also for some real scenarios, we have, for example, for power grids, we have a topology of real networks. And the aim is to use these topologies using a simulator to generate some data for that. So the structure would be from real world, but the generation of data would be used by some simulators. But the scenarios would be open source, and all the contributions that I presented here also will be open source in the GitHub repository of the project. I could share also the link if you are interested.
Yes, thank you very much. That would be very good to have these open source pieces. Yeah, I have another question if there is no from the audience, but I let people think about their questions. The other one, I think it would be related to workbench 2. I think when you presented the knowledge-assisted AI, the part in which you integrate physics. So my simple question, I hope it is simple, is from my understanding, here actually what you consider it appears to be necessarily dense, right? It is a fully connected architecture. If for technical reasons I wish to train a sparse part of this thing, would that be okay with respect to the physics, or it would not be necessarily allowed?
So here, we have the initialization of the parameters by a neural network, which is a dense network, which allowed to initialize just to have an initial estimation of the parameters. Afterwards, we are interleaving the graph neural networks, which are going to compute by the message passing mechanism the different power grid equations. So they are solving the real power grid equations by optimizing them through the message passing mechanism. And afterwards, we are also going to compute the errors with respect to the power grid equation, the constraints, for example, the conservation law. And the objective function for the neural network will be this error term, which is the difference between the production and consumption, and also the messages which is coming from the neighboring nodes. So this error will guide will guide the readjustment and fine-tuning of the parameters during the training of the parameters.
Okay. Yeah, thank you. Maybe it is still open. I'm wondering if, I mean, for example, reasons of computing resource, I would not necessarily wish to train a fully connected network like that, but try to enforce some of these connections to zero. Maybe
no, you can do that for sure. That's a version already. That's improved version of the first one that I not presented here. In the first version, we have set all the parameters to zero. It was to the network to learn them from the zero parameters. And we have shown that by have a guess at the initial step by another neural network would help to accelerate the conversions during the training. But for sure, you could, yes.
Thank you very much. Still have some questions, but yeah, I encourage people to ask. But anyway, if there is not, that means we were very clear.
And there are different deliverables also in the project that have been already published in the website of the project. If someone interested could also see them for more details. The presentation was very compact and dense, so to give you an overview and the willing to going if you want to go into more deep reading during a personal session by reading the deliverables.
Okay, so maybe I can take one for someone who asks, or as you float you talked about work package in which also have ECG signals. Yes. Is that right?
Yes.
ECG yes. Signal. And you are trying to. What is the task behind? You are trying to predict the next body motion, or what? What is the...
No, the objective here, that is the users are wearing some, for example, watches that measure their level of ECG during the operation, during the decision-making, when they are going to interact, for example, in real-world scenarios. We are going to see with respect to each scenario how they are going to behave, what is their level of stress, and we have a model that learns that in some personalized sessions from the humans. Once that learned, we are going to take advantage of this personalized model during decision making. The AI agents during the decision making could see, for example, if some behaviors of of human operators could be risky or stressful. They could detect that in real time and adjust, for example, the mode of interaction during the decision making. For example, if the human operator is very stressful, the AI agents could, for example, take some actions without requesting the human operator intervention. For example, for some risky events that should be made on time, if the human operator is very stressful, so the AI agents could adapt its behavior, or for example, to turn off some panels on the interactive AI framework, that the human operators could just focus on some important features, something like that, to guide a little bit more with respect to his cognition, charge, and stress level.
Okay, thank you very much again, Milad, for this excellent talk, and actually it covers many pieces. I see Bertrand has a question.
Yes,
Bertrand?
it's not a technical question. This is why I wanted to. I waited a little bit Milad, I think we will have the next Trustworthy AI Summit end of this year, probably mid of November in Netherlands. You probably will have some interesting results in between.
Yeah.
So just to let you know that I think it will be interesting to have some highlights of what you do during this summit. I don't know how and when, so it has to be organized, but just to let you know that we will have it and follow what we do so that you can intervene in appropriate time for being present and showing some interesting highlights of the project. I think it's very, very interesting.
Yeah, for sure, with pleasure.
Okay.
We have a validation campaign that will finish until I think end of summer. So we are going to have some preliminary results for there for more how to say, more complex experiments that require the human involvement. That could be until the end of project. So I think that should be for next year. But if there are some results on the human behavior results also, maybe I can share also at the time.
So there will be some material for Trustworthy AI Summit in 2027.
Yeah. Yes.
We have time to prepare for that. Thank you.
So we'd be excited about new results. Thanks again, Milad, for this.
Thank you very much, Milad.
Thanks to all for being here. And yeah, see you for the next seminar, which would be on February 18, same time. And the speakers will be confirmed soon. Have a nice day.
Thank you.
Thank you. Bye.
Bye-bye.